Hi, let's discuss Dijkstra algorithm. Dijkstra algorithm solve the single source shortest path problem on a non-negative weighted directed graph G equals to VA. So weight should be non-negative, means it should be positive, and the graph should be directed. If directions are not given, you can add direction to both sides. Here weight is 5. So you can consider this weight is for A to B and B to A. You can add a S like this. So A to B weight is 5, B to A weight is 5. If undirected graph is given, you can make it to directed graph. There is another algorithm, Bellman-Ford algorithm, that work on negative weighted graph. But this Dijkstra algorithm that only work for positive weighted graph. Sometimes it work on negative weight if there is no negative weight cycle present. So Dijkstra algorithm maintain a set S of vertices whose final shortest path weight from the source S. So this uppercase S is for set S and this small s is for source S. The algorithm repeatedly select the vertex U from V minus S, means which are not in the set S, with the minimum shortest path estimate. Shortest path estimate means we'll check the D value, add U to S and relax all edges leaving U. In the following implementation, we use mean priority queue of vertices keyed by their D value. So we'll maintain a queue where we'll keep all the D values. Let's see the algorithm, Dijkstra algorithm. GWS1 graph is given, source is given and weights are given. So first we'll do initialize single source GS. In previous lecture I discussed this initialize single source GS. For this function we'll do, it will add 0 to source, means s dot d will be 0 and all other vertex d will be infinite. So this initialize single source will change source vertex distance to 0 and all other vertex distance to infinity. Next, s equals to 5, initially s equals to 5, then q equals to gv, all vertices are in q. While q not equals to 5, means while q is not empty, you extract min from q. We'll extract minimum from this q. S will be S union U, will add U to set S. Then for each vertex V belongs to G dot adjacent U. So for each vertex V which are adjacent of U, will relax U V W. I already discussed how we'll do this relax in previous lecture, just go through that. As Dijkstra algorithm always choose the lightest or closest vertex in V minus S to add to set S, we say it uses the greedy technique. So every time it just add one vertex which is the closest to that vertex and it is the lightest, means its weight is less. So every time we're just adding one vertex to source. That's why it is a greedy technique. So what will be running time of it? Running time depends on this extract min. So how we are extracting the minimum? If this is a normal array, then extraction min will be order of V, order of number of vertices. This queue contain all the vertices. Now we'll compare with every vertices and which one is the lowest, that will extract. So extract min running time will be order of V if this is a array, and if this is a binary min heap, then extract min running time will be order of log V. And for every vertex we are doing this. So if Q is a array, then running time will be order of V square, and if it is maintained by a binary min heap, then running time will be order of E log V. So the time efficiency of Dijkstra algorithm depends on the data structure used for implementing the priority queue and for representing the input graph itself. So how the graph is represented and how the priority queue is maintained. If graph is represented by a weighted matrix and priority queue is implemented by a unordered array, then running time will be order of V square. And if graph is represented by adjacency list and priority queue is represented by the min heap, then running time is order of number of edges log number of vertices. It's same as Prim's algorithm. So running time depends on how the graph is represented and how the priority queue is maintained. If it is array, then order of b square. If it is a min heap, then order of number of edges log number of vertices. Let's see one example of execution of Dijkstra algorithm. We'll refer this algorithm, so I have written here. First step, initialize single source GS. Means this S D value will be 0, all other vertices D value will be infinitive. I am writing D value inside the circle. So for S D equals to 0, other vertex D equals to infinitive. So let me maintain a set S. Initially S equals to 5 and I will maintain another set Q. Q equals to GB means Q will contain all the vertices. So let me write all the vertices D value here. For S0, for other it is infinitive. While Q not equals to 5, is Q 5? No. You extract minimum from the Q. So what is the minimum? Obviously minimum is 0. Then S will be S union U. So we'll add this S to set S. We extracted the minimum value from the Q and we add it to set S. Then for each vertex B which are adjacent to U. So now which vertex are adjacent to U? T and Y. Relax T and Y. So T distance update as 10 and Y distance update as 5. Next again we'll run the while loop. While Q not equals to 5, is Q 5? No. Then U equals to extract min. Now from this we'll extract min and min is 5. Y distance is 5, so we'll include Y in set S. Then for each vertex which are adjacent to Y, we'll relax. So Y adjacent is Z, then X, then T. So T previously it was 10. Now it will be 5 plus 3. So 5 plus 3 it is 8. 10 is greater than 8. So this T value will change to 8. Next Z, previously it was infinitive, now it will be 5 plus 2, it's 7. So this Z value will update to 7. This X value will update to 5 plus 9, it will be 14. Previously it was infinitive, infinitive is greater than 14. So now distance will update. Before T distance was 10 from 0, now T distance will be 8 from Y. So via Y, this distance of T is less than direct distance. So that's why we update this path S to Y and Y to T. Now Q contain 8, 14 and 7. So from these three, which one is the minimum? Obviously minimum is 7. In extract min, we'll extract 7 and this vertex Z will add to set S. Then for each vertex adjacent to Z, Z adjacent is this X. Now I'll relax this X. X weight is 14. Now via Z, it will be 7 plus 6. So 7 plus 6 is 13. Is 14 greater than 13? Yes. So this X will be updated to 13. Now after updation, we got this. Just mark previously for X, we considered the path from Y to X. So this 9 was shaded. Now from this Z to X is shaded. As by this path, this X value updated. Now Q contains just 8 and 13. So from this 8 and 13, which one is the minimum? Obviously 8. So in extract min, we'll extract T and we'll add T to set S. So adjacent of T are X and Y. X weight is 13. Now 8 plus 1. 8 plus 1. Obviously 13 is greater than 8 plus 1. So we'll update this X value to 9. Now 8 plus 2, it's 10. 5 is less than 10, so no update. We'll just update distance of X. So after updation of X value, now we got this graph. In Q, there is just one vertex, weight is 9. So next we'll include that. Now this is the final shortest path as Q is empty. We included every vertex. Now check the shortest path. S to Y, cost is 5. Then S to T via Y. So S, Y, T, cost is 8. Then S to Z. So S, Y, Z, cost is 7. Next S to X. So S, y t x. Cost is 9. We are not only finding the shortest path weight, we are also finding the path. So from S to Y direct path, then S to T, S to Y, then Y to T. S to X, S to Y, Y to T, then T to X, S to Z, S to Y, then Y to Z. So now let me write all D value and pi value. So S dot D equals to 0, Y dot D equals to 5, and y dot pi means predecessor, from which vertex you reach to this vertex. So it's s. T dot d equals to 8 and t dot pi equals to y. From y you are reaching to t. Next x dot d equals to 9. X dot pi will be t. Z dot d equals to 7. Z dot pi will be y. In today's lecture, I discussed Dijkstra algorithm with one example. In next lecture, I will discuss one more example. And if this lecture is helpful for you, please like, share and subscribe. Thank you.